Hey everyone, and welcome to today's Explainer. It's absolutely wild to think about, right? In an era where we literally have space travel and instant global communication at our fingertips, the fundamental shape of our planet is still a hot topic of debate for some folks. And the crazy thing is, this isn't happening because we lack evidence. Not at all. It's actually a fascinating look into human psychology, how we process information, and how we build trust in a world that is just overflowing with competing claims. So today, we're going to unpack all of this using the incredible power of pure observable measurement. Here is our roadmap for today. We're going to look at the enduring debate itself, check out some ancient proofs of the curve, dive into Earth's actual mathematical shape, and then explore some observable DIY evidence you can find right outside. After that, we'll see how modern tech practically demands a globe, and finally, talk about navigating the information age. We're going to build an airtight case, step by step. All right, let's jump right into Section 1, the enduring shape debate, and why we even still ask. Science, right? It isn't just this static list of facts handed down by authority figures. It's a living, dynamic process of observation, which leads us to a pretty big question. Why, in a modern world totally saturated with information, does humanity still grapple with competing claims about the very ground we stand on? Honestly, it's completely valid to be curious. When we're constantly bombarded with endless theories online, it is entirely natural to want to test reality for ourselves. Curiosity is the engine of science, provided we're actually willing to follow where the measurements lead us. Moving along to Section 2, Ancient Proof of the Curve. This is all about millennia of measurement. Understanding our planet's shape isn't some new age thing. It's a shared human achievement dating back thousands of years. Long before cameras ever left the ground, ancient thinkers beautifully turned philosophical ideas into hard, repeatable geometry. Way back in the 6th century BCE, Pythagoras proposed a spherical Earth, but it was observation that really cemented it. By the 4th century BCE, Aristotle observed ships disappearing hull first over the horizon, and he realized the Earth's shadow during a lunar eclipse is always a perfect curve. Then, around 240 BCE, Eratosthenes calculated the Earth's circumference to an incredibly accurate degree using just simple geometry and the shadows cast down a well in Syene versus Alexandria. Amazing, right? And by the 9th century, during the Islamic Golden Age, Caliph al-Ma'mun organized teams in Mesopotamia to refine these measurements with precision instruments. This is truly a global, shared scientific triumph. Which brings us to Section 3. Earth's true mathematical shape, because it goes beyond just a simple sphere. Okay, so saying the Earth is round is actually just an approximation. Technically speaking, our planet is an oblate spheroid. Because the Earth spins, the centrifugal effect pushes material outward at the equator, where the rotational speed is a staggering 1,670 kilometers per hour. We also have to talk about the geoid. See, because our planet has rugged mountains, deep ocean trenches, and varied crust densities, gravity isn't perfectly uniform everywhere. The geoid is essentially this undulating, bumpy shape the ocean surface would take under Earth's gravity and rotation alone, totally ignoring winds and tides. It's wonderfully complex. So just how much does the Earth actually bulge? Exactly 42.6 kilometers. That's the precise difference in width between the Earth's equatorial diameter and its pole-to-pole height. This tiny little extension results in a flattening ratio of just 1/298. To our human eyes, that means the Earth is exceptionally smooth. Like if you scaled the Earth down to the size of a billiard ball, it would literally be smoother than a perfectly polished cue ball. But precise measurement reveals this beautiful, subtle oblateness. Let's dive into Section 4, observable evidence all around us. It's time for some DIY science. So how can we prove this curvature without, needing a multi-million-dollar rocket? Let's tackle the biggest misconception right out of the gate. If the Earth is a globe, why does the horizon look completely flat when we step outside? Well, it all comes down to scale. If you're standing on the ground, let's say at about 1.7 meters tall, your horizon is only 4.7 kilometers away. The actual drop across that specific distance is just a few meters. This tiny angular deviation from a straight line is entirely below the threshold of human perception. The planet is just so massive that any tiny segment we look at on our human scale is naturally going to appear perfectly flat. True curvature really only becomes visually obvious when you get up to really high altitudes, like in a commercial airplane or a weather balloon. Okay, here's another fantastic question we see thrown around a lot. If we live on a spinning globe, why doesn't the water just fall off the bottom? The answer is literally grounded in the fundamental physics of gravity. You have to remember, down is not some absolute direction in the universe. Down is simply defined locally as toward the center of the Earth's mass. Because the Earth is roughly spherical, that direction is radial. Every single drop of water in the ocean and every single person standing on the surface feels the centripetal pull drawing them toward the core. Water curves around the planet simply because all its molecules are being pulled toward that exact same common center. And hey, you can actually test this spherical geometry yourself. Try this DIY maritime experiment next time you're at the beach. First, lie down right at the water's edge and pick out a visual marker way out on the horizon. Second, stand up and look again. You will instantly observe the horizon has visibly moved farther away, revealing things that were previously hidden by the curve of the water. Finally, if you ascend a tall hill or building nearby, the distance to the horizon increases measurably based on a simple mathematical formula tied to spherical geometry. It's a totally reproducible test anyone can do.
Moving into Section 5, Modern Tech Demands a Globe. Let's look at the geometry of our daily lives.
We've talked about ancient wells and horizons, but guys, our modern infrastructure literally relies on this shape to function. When you fly from LA to Tokyo, the plane doesn't just fly a straight line on a flat map. It arcs way up north, hugging Alaska. This great circle route is mathematically the shortest path on a sphere. Or think about geostationary satellites. They're placed exactly 35,786 kilometers above the equator to orbit at the exact rate of Earth's rotation so they can deliver your TV signals. The International Space Station circles a globe every 90 minutes. Even the undersea telecom cables that route our internet traffic rely strictly on a globe model for their latency and signal timing. Let's actually dive into one specific piece of tech because it's probably in your pocket right now, GPS. The Global Positioning System relies on a constellation of at least 24 satellites. To triangulate your exact position on a map, the system explicitly has to account for the oblate shape of the Earth's gravity field, as well as Einstein's theory of general relativity. If the Earth were flat with some different gravitational law, the entire orbital mechanics and signal propagation of the GPS on your smartphone would instantly fail. Period. It works seamlessly precisely because our model of the Earth's shape is correct.
Which brings us to our final section, Section 6, Navigating the Information Age and the Importance of Critical Thinking.
So how do we process all this competing information and actually build foundational trust in scientific consensus? Well, we have to clearly differentiate between evidence and opinion. Evidence is observable, it's measurable, and most importantly, it's reproducible by anyone under the right conditions. And opinion, on the other hand, might be a very strongly felt belief, but it absolutely cannot change the outcome of a physical measurement. To combat our own natural confirmation bias, we've got to evaluate our sources and prioritize reproducible experiments over unverified claims. The fact that pure geometry gives the exact same answer no matter who performs the test is incredibly powerful.
It really all boils down to this quote: "The shape of our world is not a matter of belief, it is a matter of measurement." From Eratosthenes back in antiquity all the way to the GPS navigating your car today, this massive interlocking body of evidence proves our home is a beautiful, subtly flattened sphere. Genuine inquiry means we test, we measure, and we gracefully accept the reality that emerges from the data. Which leaves us with one final question for you today. Are you ready to step outside and measure reality for yourself? There is an entire universe of observable science waiting for you, right in your own backyard. Thank you so much for joining me on this explainer. I really hope you walk away feeling empowered with this knowledge. For more, visit our website, Fair Solution.